Hello, universe. So I was working with some students today, and we discussed a really important topic which I wanted to share with you all here. So the idea is the structure of proofwriting, especially for when you're first learning how to prove things in math. So typically speaking, the structure of proof, you begin with certain assumptions, certain mathematical assumptions, and these are certain properties usually that you're supposing about whatever object you're studying. And they are going to have all of these assumptions, all of these properties that you're assuming to be true are going to have very precise mathematical definitions and intuition. And then you want to end up with some conclusion, which again, the conclusion is going to be a series of propositions or mathematical properties which you want to show are true given these certain assumptions, okay? And these different properties might be connected, as you can see here, like the puzzle pieces, they're going to be connected mathematically. Now, the proof basically requires you to complete this puzzle and form a connection between the assumption and the conclusion. Of course, this isn't a perfect analogy because you ultimately want to show that the assumption implies the conclusion. But in order to kind of connect this puzzle together, it may just immediately connect together. And in fact, the picture that I've drawn here was supposed to be simple enough where actually if you just took this vertical column of assumptions and you just directly connected it to the conclusion puzzle pieces, you would get an answer. You could immediately connect the assumption to the conclusion. And a lot of times when you're just first learning math, you won't need many puzzle pieces in between this gap here. It's usually going to be maybe one or two puzzle pieces that you need to find and outsource that are not just handed to you. But most of the time you're handed the assumptions, you're handed the specific nature of the conclusions, and then it's just a matter of literally taking these two vertical columns and sticking them together in a rigorous way. However, for a more complicated proof, you're not just going to be able to immediately link the assumptions to the conclusions. You're actually going to have to use lemmas, tools, and other mathematical theorems and or calculations. And so all of these other calculations, tools, and lemmas, I'm viewing them as kind of other puzzle pieces that kind of go somewhere in the center here of this diagram. And these puzzle pieces are being used to connect the assumptions to the conclusions, okay? And sometimes in math, when you're doing research, you don't actually know what these assumptions and conclusions are exactly, and that the first step is to actually build or discover what these assumptions and conclusions should actually be. We're kind of taking for granted in this diagram that you're actually handed a set of assumptions and you're handed a set of conclusions, and you know that such an implication, such a proof exists, and so your goal is to find it. In research math, of course, these assumptions and conclusions are on much shakier footing, and it's actually a huge problem and a huge skill to be able to actually put these assumptions and conclusions together in the right way before attempting the proof. But when you're just first learning math and you're taking courses, etc., you're going to be handed these assumptions and these conclusions, and your task is to bring them together, potentially in a more advanced course using other puzzle pieces in the middle here. And these other puzzle pieces you're going to have to find by reading the textbook, by understanding the material, by understanding what's relevant, what theorems are relevant to the problem, what sort of tools are relevant to the problem. And so you're going to have to find these puzzle pieces on your own and rotate them and fit them in the right way to connect the assumptions to the conclusions in your proof, okay? And so I wrote here, I said, beginning students ought to write out explicitly the assumptions and conclusions of the problem in full mathematical detail, alongside any theorems and tools which may be useful in the proof. These definitions and theorems must be understood, not simply memorized. Okay? So, in a mathematical problem, I should never, if I'm tutoring you, if I'm teaching you foundations of analysis, I never want to see your paper blank, okay? Because almost always you're going to be given a set of assumptions which you can write out explicitly the mathematical definitions of each of these assumptions. And if you're first learning math, it's a good exercise just in memorization alone to be able to just write out these assumptions. But as I emphasized here, you shouldn't just memorize them. Of course, you should memorize theorems and proofs, etc. But memorization alone is not enough. You need to understand what they mean and understand where they come from, okay? So once you've written out all of these definitions and assumptions that you're going to need for the problem in full mathematical detail, and once you're sure that you understand conceptually and intuitively what they mean, I want you to do the same for the conclusion. Okay, so the conclusion that you want to reach is also going to be a set of mathematical kind of definitions and properties that you're going to be able to write out explicitly because they're handed to you in the problem. And so you can source from your textbook or from the internet or wherever and kind of write out these definitions explicitly before even attempting the problem. And you need to make sure you understand these definitions as well before attempting the problem. And then finally, oftentimes they're going to be clear, like obvious, not obvious, but sometimes, if you're lucky, there's going to be some theorem or some lemma that is clearly of use to you. And that should just, it'll take time to build the intuition, and sometimes it's totally not obvious, right? Math is not easy. It's not an easy subject. But many times there will be a very clear puzzle piece here, maybe a very clear tool or theorem that you've covered in your class or that you've read in the textbook that is going to be an essential ingredient in joining the assumptions to the conclusions. And so if you suspect that, when you write out all these assumptions, you write out all the conclusions, and you think about what the problem is really asking you and understand the question that the problem is asking you before attempting to prove it, then it's probably going to become apparent that there might be a theorem that might be of great use to you. And so then I want you to write out that theorem and that lemma in full detail as well, in full mathematical detail as well. And I want you to write it, of course, in the context of the problem, okay? But not only write out this theorem, this key ingredient, this lemma, or whatever it is, make sure you understand what it's saying as well. Anytime you write out a definition, anytime you write out a theorem, I want you to make sure that you understand what you are writing. It's not just some complex juggling of epsilons and deltas. Sorry, my cat's playing with the plastic. It's not just some complex juggling of epsilons and deltas, okay? These are deep geometric ideas, right? Like oftentimes the definitions that you're writing out, the theorems that you're writing out, they have an intuition, a deeper meaning to them. And they're saying something about the world. They're saying something in simple terms. They're saying something simple, but in a complicated way. Okay, so these definitions about continuity, about the epsilon delta definitions of continuity, are a perfect example of something that seems totally contrived, totally overcomplicated, and almost encyclopedic to a beginner. But once you have more familiarity, and when you think about this definition, what it's saying in the epsilon delta definition of continuity, right? You can understand that this definition is telling me that small perturbations in the input result in small perturbations of the output, right? So the function preserves locality in the sense that if I have some small change in my input, continuity tells me that the output of the function will undergo a relatively small change with respect to how small the perturbation of the input was, okay? And of course, the geometric interpretation of continuity is far more nuanced than this. I'm not claiming to fully capture that in like a few sentences. I'm just saying that, you can't just accept the epsilon delta definition as just handed to you on a golden platter without really thinking about what is it saying, who came up with this, and why. How did somebody just come up with this epsilon delta definition? It didn't just pop out of the universe from nowhere. It didn't just pop out of the sky. Somebody came up with this definition. What were they thinking about? What is the motivation, the intuition behind where this is coming from? So the last thing I wanted to provide you with is a quick example, okay? So the example is, show that f of x equals x squared is uniformly continuous on the interval 0, 1. Is it uniformly continuous on the real numbers? Now, I'm not going to provide a proof of this statement, but rather I'm going to show you, I've included two kind of things that if I'm tutoring you in Foundations of Analysis, you need to have these already written out on your paper. Maybe the second one is a bit non-obvious because this is an actual calculation, but this first thing that I've written here, okay, is the definition of uniform continuity. So I expect this definition to be written on your paper. Before attempting this problem and before asking questions about this problem, I expect this definition to be written on your paper because we see here in this question, it's asking about this function being uniformly continuous. So that's the puzzle piece that we're looking at here, is uniform continuity. So we need to understand what uniform continuity means. And the first step towards understanding what uniform continuity means is writing out the definition, okay? All right, and you can write it out from memory, you can have it memorized, but then I'm going to ask you, beyond just your memory, what does this mean? What does this epsilon delta definition mean? Why is this the case? Why is this what we call uniformly continuous? Okay? And I want you to think about that, and think about it on your own and wrestle with that question. And I've posted some videos on uniform continuity. I've posted some videos explaining some geometric intuition on uniform continuity. So if you want to hear my perspective, then you can go to my Foundations of Analysis playlist and look that up. But what I'm emphasizing is I want you to think about it on your own and think about it and ask yourself, what does this mean? And it's not just this definition, it's every definition that you come across in math that you're using, like, ingredients in this recipe that you're, chefing up a theorem. I need you to understand what they mean. And then, for a question, for the second part of this question saying, is this function uniformly continuous on R? You're not going to be able to answer that question very easily if you don't understand the geometric meaning of uniform continuity. For example, I can tell you right now that x squared is certainly not uniformly continuous on R because its slope is going up to infinity. And if a function is sufficiently regular, sufficiently differentiable, then, if its slope is going off to infinity, and it's going off to infinity in over a set which is unbounded, okay? So over a set which is unbounded, like the real numbers, then the function cannot be uniformly continuous because if I just think about, okay, yeah, actually I'm too obsessed with math where I'm gonna explain this to you right now instead of ending the video like I should. Yeah, okay. So basically, I don't want to just present this definition without explaining to you. Basically, the idea is that if you look at the graph of a function, okay, so let's picture the graph of a function, then the modulus of uniform continuity is the place where the function, intuitively speaking, if this function is smooth and it has a derivative everywhere, then the modulus of uniform continuity is precisely the modulus of continuity where the slope is the greatest, okay? And the reason for that is because continuity, slope, the tangent line locally measures how much the function stretches or compresses intervals. And so if I look at the domain, this is the graph of my function, okay? Here's my domain. Then if I look at a small ball here, okay, and I look at the image of this small ball under the function, it's going to be a ball in the codomain, right? If I just kind of draw this out like this and like this, then the image of the function is also a ball here. And that ball locally, if this input ball is small enough, this output ball is locally stretched by a factor which is the slope of the function, okay? And so when I'm asking questions about uniform continuity, and of course this is a huge oversimplification because we're assuming differentiability, which is stronger than assuming continuity, but it's good for the sake of intuition. So then the idea is that, if we want a modulus of uniform continuity, okay, so if we want an ability to bound the range of the outputs of this function for a uniform input ball radius, then we simply need to slide this input ball around. This input ball is of a fixed width delta, and the output ball needs to be of a fixed width less than epsilon. Okay? So the output ball needs to be of a width less than epsilon when I input a ball of radius delta into the function. And so I can slide this ball around And when I slide this ball around, I'm going to get different outputs with different radii. But I need, for uniform continuity, I need that all of the output balls have a radii which is bounded uniformly above by epsilon. Okay, so for the same delta, for the same value of delta, I can slide this input ball wherever I want, and the output ball, the range of the output values, needs to always lie within epsilon. So to find the modulus of uniform continuity, I simply need to go, if this function is differentiable, I need to go to the place where its slope is the greatest. And when I go to the place where its slope is the greatest, then I can find a delta such that the output ball is of radius epsilon. And once I find this delta will actually automatically work as a uniform delta modulus of continuity, because I can then slide this ball around, and when I slide this ball around, the output ball will only be of smaller radius, right? Because I've chosen essentially the worst case possible point where the function stretches an input interval by the most, right? By the most, because the derivative is, remember, the derivative measures a stretching factor from the local volume distortion from the input to the output. Okay, and so here, right, when this question asks me, is it uniformly continuous on all of R, I immediately know that it's not, because you know, f of x equals x squared, it's on an unbounded domain, so it's going all the way out to the real numbers. And if I keep looking at an input ball and sliding that input ball to the right, further and further down the real line, mass will get stretched by a factor of 2x, the derivative of x squared. And so the length of this input ball is going to get stretched by a larger and larger factor the further out I go along the real axis. So I know that there's not going to be a uniform delta, because if I fix any delta here and I slide the ball far enough out on the real numbers, the output ball is going to be of arbitrarily large radius, and that's just due to the fact that the real numbers are unbounded and the slope of this function is going to infinity as you get further and further on the real axis. Okay, so anyways, sorry to rant on this, but basically, I want you to know this definition on the back of your heart, know this definition instantly and be able to write it instantly. But then if I ask you, what does this mean? This is way more important, that you better be able to tell me what this definition means. And you better be able to, on the spot, without looking it up, without doing anything, be able to explain, what does this definition mean? Why is this definition constructed the way that it is? And if you can't give that explanation, that's okay. You're still learning. Everyone's still learning. I'm not trying to be an elitist here. I'm just trying to tell you that if you don't know what this definition means, then that should be the first thing that you study before you try to prove this example. Before you try to go on and prove this, you better study what this example means and understand what it means. Just having the definition is not enough. You need to understand what it's saying. If you don't understand what it's saying, then you're like looking at a blurred puzzle piece. You're like looking at something that's super blurry. Imagine if I just blurred out this diagram here, and then I ask you to solve the puzzle. Well, you can't solve the puzzle. You don't know. Maybe you'll get lucky, but if you don't see this clearly, if you don't clearly understand how these assumptions fit together and what's going on in these definitions, geometrically, intuitively, algebraically, etc., if you don't understand these assumptions beyond just memorizing the definitions, how are you supposed to complete the puzzle? You are at a complete loss because you don't have access to the amount of the wealth of information and the understanding of what these puzzle pieces mean and their context and how they fit together. If you don't understand the context, you don't understand how they fit together, how could you possibly complete the puzzle? Right? And one last thing that I'll mention is that for this specific example, for the first part, uniformly continuous on 0, 1, there's another tool that you could use where if you've been studying real analysis, let's say you've studied foundations of analysis, you could actually identify a lemma that might be of help to you. You don't need this lemma, but it could be of help that, in fact, continuous functions on compact domains are uniformly continuous. Okay, so we could write this here as another lemma here. Continuous functions on compact sets on compact domain are uniformly continuous, right? Okay, so I'm going to write that out, and obviously you should write it out in way more detail than I just wrote it out. You're going to need to write out, okay, if I have a continuous function on a compact domain, that's uniformly continuous. And when you write this out, you better understand, what does it mean to be compact? What does it mean to be continuous? What's a compact domain? And then why are continuous functions on compact domains uniformly continuous? Why is that true? That's a proof, that's a whole theorem on its own. So hopefully, if you're going to reference this lemma and use it in your proof, obviously this makes the example much more trivial, because then you just say, okay, well, 0, 1 is compact, and x squared is continuous. You probably need to show that x squared is continuous, but if you can take for granted that x squared is continuous, then since 0, 1, since the domain is compact, then by this lemma, automatically f of x equals x squared is uniformly continuous. So it makes the proof a lot easier. But if you're going to use some heavy machinery like this lemma, then you'd better understand the proof of this lemma. You can't just use this lemma without understanding where it came from and why it's true. If you're just going to pull out this lemma from your textbook and be like, oh, this makes the proof easy, because I can just use this lemma, but you've never read the proof of this lemma, you don't understand why this lemma is true, that's bad math. That's not going to be conducive to learning, because you're just using a tool that you don't actually understand where it came from. Okay, so if you use this lemma, it's going to make this example a lot easier. However, you'd better understand where it came from. The last thing that I want to mention, and then I'll let you all go. And if you all made it this far, I really appreciate you listening to these videos, and I hope you learn from this. And obviously, I'm not an expert mathematician. These are just the things that I try to tell my students, and some of the things that I've picked up throughout the years. But I'm not claiming to have all the answers here. So for this last section that I wrote here, this last section is a bit of a calculation, okay? So it's a calculation which uses this relevant definition, and namely, I'm looking at f of x minus f of y, and I'm writing it out, and I'm writing out what f of x is. F of x is x squared, f of y is y squared. And so I'm looking at this f of x minus f of y less than epsilon, and I'm unpacking that. And specifically, I'm unpacking it algebraically, okay? So I unpack this expression algebraically by factoring x squared minus y squared, okay? And then, I can bound x plus y above by 2 because x and y belong to the domain 0, 1. So I can bound this x plus y above by 2. And then this x minus y, I can bound it by delta, right? And then choose my uniform delta to be epsilon over 2. So this kind of scratch work here, I won't go through the details of the proof, but this sort of algebraic scratch work is what you're going to need before you start the proof, because this is like the heart of the algebraic argument to make the proof rigorous in this example without using this lemma on the bottom, this lemma on the bottom is like a shotgun, makes things way too easy. But if we ignore this for a moment, then yeah, this algebraic calculation here is exactly what you're going to need to show the uniform continuity of x squared algebraically. But what's interesting is that you could, if you're just a beginning student, you could write out this definition, you could write out this algebraic calculation, and then solve the problem perfectly and get full marks, get 100%, but never actually answer this question in orange. What does this mean? So if you've written out the definition and you've written out some scratch work, and then you prove the question algebraically, and you show and you connect the puzzle piece together successfully, you connect the puzzle together. Turns out the puzzle's not actually that bad in this case. I can just take these two puzzle pieces and just connect them directly onto the other two, algebraically, right? The problem with that is that there's this question which begs to be answered, which is, what does this mean? And if you don't answer this question, what does this mean? Then why are you even attempting to solve the puzzle in the first place? You don't even know what this puzzle means. You don't know why you're trying to put these puzzle pieces together. Okay? So the most important question is this: what does this mean? What does this mean? I want you to ask that question over and over again to yourself. And make sure that you really, really ask this question, okay? Beyond just from a definitional perspective. I don't want the definitions here. I don't want just the definitions. I don't want you to answer what does this mean by telling me the algebraic definition. I want you to tell me what does this mean intuitively, geometrically. What is it saying about a function? What is it saying about the world? Why do we have this definition? Why do we care about uniform continuity? Why is it a useful thing for us to study? What applications does it have maybe to the real world? If you're creating a mathematical model, why would you want a function to be uniformly continuous? What good does that do you? Okay, so this is just kind of a brief overview of some topics that I went through with my students today, and I hope you got something out of this. So thanks. Have a nice day.